Hi guys, my name is Lou and I am a research assistant and the lab manager at the Molecular Neurobiology Lab at the Salk Institute. Our lab studies behavior and how your brain actually processes behavior, and we are led by our fearless leader, Dr. Chalasani, who we all just refer to as Shrek. So we're going to tell you about a project that Natasha worked on this summer.
Hi guys, I'm Natasha. I'm going to be starting my senior year at the Bishop School. I plan on either studying neurobiology or genetic engineering, and I'm really excited to talk to you guys about my project.
So Natasha, why don't you just tell us how you got here in the first place?
Sure. So I was one of 12 interns that got to experience what it's like to work in a lab through the Heithoff-Brody Scholar Program. And it was an 8-week kind of thing that started off with 1 week at boot camp, which led into our lab experience.
So Natasha, do you remember what it was like the first week that you started in the lab?
It was kind of overwhelming. I took a look at the shelves and immediately thought, there's so many things here, so much stuff going on, and our lab is pretty busy. Like, there are a lot of people here and just a lot of commotion and movement.
And what did you do once you actually got into the lab?
I worked on the Autism project, which you know all about.
Yeah, so the Autism project that Natasha mentions is a big project that we've worked on in our lab. And the point of the project is to find a drug target that can help with the behavioral changes that kids with autism experience. So what we're doing is we're testing a library that has about 1,200 compounds that are known to be pharmaceutically active. And the goal is to hopefully find a drug or a treatment that can help kids with autism better their behavior. So in our lab, we actually use worms as our model organism. And I know you're probably thinking like, ew, gross worms, and you're thinking about the ones that are like this big and slimy and not that appealing. We actually use really, really small worms that are called C. elegans, and they grow on these small petri dishes. So it's really, really convenient for us to use them. And Natasha's gonna tell you some of the other reasons that we use C. elegans in our lab.
It's a great model organism because its genes are similar to humans, and they have 302 neurons versus the 86 billion in a human brain.
So Natasha worked with these worms throughout this whole summer. And aside from learning how to pick them and how to grow them, the most important thing she had to learn was about their life cycle. These worms have 4 larval stages, L1, L2, L3, and L4, and a 5th adult stage. And we do our experiments on day 1 adults. The biggest thing that you need to understand when you come into a lab is that you just don't show up and start doing experiments. There's a lot of prep time that goes into it, and since Natasha was only here for 8 weeks, she really had to kind of hit the ground running and just kind of take all the information that I was throwing at her and just roll with it. So the hardest thing that Natasha had to get down was her timing, because if you don't have day 1 adults, you can't do your experiments that day, and then you're just sitting around and kind of feeling hopeless.
Not having much to do.
So the very first thing that she had to learn was to make sure that she had adults every 5 days. Autism is like this big mountain to climb because it's so huge, it's so big, it affects so many people. And it's really hard to, say this is exactly autism, that's why they call it a spectrum. And what we're trying to do is really target something that we know that specifically and genetically can contribute to this autism diagnosis. So we really want to find something specific that can help these kids and not have them, taking high doses of these crazy antidepressants or other medicine that are really not gonna help in the long term and are just kind of curbing an effect in the short term.
Can this drug screen be applied to other genetically linked diseases? The answer is yes. So if this drug screen does work, it can be useful for other diseases such as Alzheimer's, schizophrenia, and more.
Okay, so how are you gonna measure behavior? You don't measure behavior as easily as you count something or as you do various steps. So what we do is we measure behavior through a drop assay. And do you want to kind of explain what the drop assay is?
The drop test consists of having 10 day one adults on a plate and then dropping a copper sulfate solution in front of the worm to see if, when it sticks its head in, whether it will reverse or not.
And why do we use copper?
The reason that we use copper is because it's a heavy metal, a toxin, and a wild type worm will react to it by reversing versus a mutant may or may not reverse.
So, in the worms, we actually focused on 3 genes that are actually found in humans. The 3 genes are neuroligin 1, neurexin 1, and SHANK1. Neuroligin and neurexin are found in the synapse, and SHANK1 is a protein that is recruited in the postsynaptic cell. Neuroligin, in cases of autism, it's been found that about 2% of kids have these genes mutated. So the really cool thing that we can do is put this gene into the worms and then test the worm's behavior that can in turn mirror back human behavior. So we're gonna go through the general steps of prep before you can actually even get your experiment started. So we make our own plates and get them ready for the experiment. What else?
We needed to have the copper sulfate solution done and the plates with your day one adults.
And then on the day of your experiment, you want to make sure that you have all your components. You want to make sure that you let your plates come to room temperature. If they were in the cold room, make sure that your concentration for your copper solutions are correct. And if you are doing a drug treatment on the day of your experiment, you want to get started early so you're not here until 6 or 7 p.m. So one of the most important things that we're doing when doing these drug tests is trying to decide what constitutes a hit, which means a behavior change after the drug treatment. So it always is going to vary a little bit from the background research or background data because no 2 worms and no 2 people are the same. But so we determined a threshold where if the percentage change was above 40% or more, we would consider that a hit. And I believe you got 1 hit, correct?
I did get 1 hit. We established that the wild type reversal rate was around 80 to 90%, and my mutant was around 40 to 50%. So the hit that I got changed a 40% reversal rate into an 80% reversal rate.
And did you do any more background on that? Did you
Yes.
change the concentrations? What did you do after you got a hit?
So once I established that it was a hit, I then did a concentration gradient, which was doubling the drug and then halving the concentration of the drug.
And what did you find when you did that?
So what I found was that doubling it and then halving it was not the correct concentration. So the reversal rates were around 40 to 60%.
All right, and so once we've collected all this data, I assume it's in your lab notebook, but I assume you have this chunk of data. So what do you do with it?
So how we recorded was using a little set that you would either put a check or an X to see a check was reversal and then an X was not a reversal. So then what we did is we took all of that data, put it into Excel, made bar graphs out of it to be able to see what the reversal rate was.
Natasha has collected all of her data. She's made her bar graphs, as you've seen. So what would be your next step in this experiment? You're staying on in this lab, so what are you gonna do?
So I would continue drug screening, so seeing more drugs, and then with the drugs that we have and the hit that I have would be further exploring the concentration gradient, the incubation period, as well as the toxicity of this drug.
And so can you explain those three that you mentioned? So the concentration, the toxicity, and the incubation time?
Sure. So the concentration gradient would be the right amount of the right dosage to give the worm. The toxicity is if it's too toxic to the worm that it might end up dying, or it might affect even its locomotion. And the incubation period is just seeing the metabolization, which would mean that it would have taken effect on the worm.
Okay, that's really cool.
So Lou, I got a hit. Does this mean that we can just start giving the drug to a little kid?
Well, what do you think?
Most likely not.
Well, no. So unfortunately, even though all of these compounds are approved by the FDA for human consumption, we can't necessarily just go ahead and give it to people to treat autism just yet. The first step will most likely be giving it to another model organism and testing the effect, most likely mice or rats. And then from there, we would move on to talking about a clinical trial and doing some of the background kind of research with the drug, and then doing a second phase trial to get it into treatment for autism or autism spectrum disorders. So I think we're just about at the end of our presentation to you guys of our experiment.
Well, I'm really grateful for this experience, and I actually didn't know that, being a high school student, you can actually do this kind of thing, and it's kind of mind-boggling still that I'm gonna be able to continue working in this lab and continue working on this project. That means a lot to me, and I'm just really, really thankful. Yeah.
Well, that's all our time, guys, so have a great day.
Bye.
Thank you.